Project for system dynamics and controls is the air noise damper. This project came about because of my senior design project is a magnetic levitation fan, and the idea is that they've on the actual magnetic levitation fan that's out there right now, they were able to fix the motor noise, which allows them to increase the amount of RPMs, but then they just gave up on the air noise because it was a little bit more problematic trying to reduce or eliminate completely what the air noise that comes out of the magnetic levitation fan. Sound waves. Air is not always noisy. Different sounds are made as a result of air. Some are melodies, while others are disturbances. Like as you can see with the flute, people blow air through flutes and trumpets and other instruments of that nature to like create melody. But then at the same time, with helicopters and fighter jets, they have to like use them in areas where there are not too many people, or it's act as disturbances because of not just the dangers that comes with the blades, but also the noises that it generates. And with the a fun fact is that even with the airplane, the turbine engines, they're in such cases because those cases of those that container also acts as a way to like muffle the sound that would be louder without the outer body of the turbine engine. Longitudinal sound waves are longitudinal sound waves as waves are sound waves in the air. The wave is characterized by a series of alternate refractions and condensations as shown. Regarding variability, there are two types of fans on the market, PMWs and non-PMWs. PMW stands for pulse modulation, which is a way for fans to be like controlled more. Usually with non-PMW DC motor fans, which were the first, fan speeds couldn't really be controlled. They had the maximum depending on the amount of volts, usually 12 volts, that was induced into the fan. But now with the PMWs, it allows for like more extensive controls, either to add increase RPM or reduce RPM. This is done with the PMWs. This uh, this this function is gained by using magnetic levitation in between the fans to reduce friction and increase the heat endurance, and this also adds an ability to the magnetic levitation fans, because now that the motor noise have been gotten rid of, the fans can have an increase in RPMs. But then the magnetic levitation fans gave up on trying to reduce the fan noise, and this may be because of the variability that comes with it. As fan noise increases, the more the RPM speeds, and they know because of the function of the magnetic levitation fans and what it allows, people want to take it to the extreme. So instead, they just give up on trying to reduce it. For the equations I'll be using in this process, because I'll be analyzing different data from different research that has already been done on the idea of how to understand the noises that come out of air, and to be able to use the research to be able to combine the research to determine the best way to reduce air noise, since there are different ways that have already been found, but because there hasn't been like a comparison between them, there hasn't been a more used idea. The free vibration of an undamped solution start with the initial condition at t is equal to 0, xt is equal to the area at is equal to the x naught, which is basically the differentiation of it is the natural frequency times the area times the differentiation at is equal to the differentiation of x naught. The solution is the x naught. The solution for the position is the x naught times cosine the natural frequency times time plus the differentiation of x naught divided by the natural frequency times sine of the natural frequency times time. This then results in xt being simplified to the solution form. Xt is equal to a times cosine natural frequency times t subtracted from phi. Using the relation a1 is equal to a naught cosine phi naught, a2 is also equal to a naught sine phi naught, xt is then equal to a naught sine natural frequency times time plus phi naught. A naught is then derived to be the square root of x naught squared plus x naught plus the square of x naught divided by the natural frequency, and phi is equal to the inverse tangent of x naught times the natural frequency